The Commodore 64 power supply has killed more home computers than any other single component ever produced. Its reputation as a cheap and destructive component should be enough to convince people not to use them, but they continue to do so. So what makes this the worst power supply ever created? In this episode, we will explore the infamous Commodore 64 power supply.
Thank you for joining me for my most classic artistic introduction of the year. As we discuss the Commodore 64 power supplies, notorious for destroying Commodore 64s. Before we go into the power supplies and how terrible they are and the fact that they destroy computers, there's, a couple things to be said about the plug and pray philosophy of taking old equipment in general, plugging it into a wall and hoping for the best. And I think it's interesting to point out before even getting started that at best, these weren't very good power supplies. And now, getting on 40 years later, people go and pick up an old computer like this. And even if they didn't know that the power supplies weren't very good and the shortcomings about protection of these power supplies, taking anything that's 40 years old, 50 years old, 60 years old, and simply plugging it into the wall 120 volts or 230 if you're in Europe, and just expecting it to work and not having fire come out of it or destroy something that's really sensitive, is foolish to think that that's not going to happen. I have all sorts of different pieces of gear here, and each and every one of these I could plug into the wall and turn them on, and they're going to work just fine because they've all been restored. But at some point, when I got them, there was no way I would have plugged them in. And if I did, it probably would have caused irreparable damage because unlike the Commodore 64, the power supplies are built into these units. And there's just a cord that comes out the back. And you plug them in, and generally, there are capacitors that are shorted, electrolytic capacitors that have issues in gear like this that's, 70 years old, 60 years old. And when it gets that electricity and the capacitors are broken down, smoke comes out and it takes down all sorts of things with it, amplifiers and test gear and what have you. It's generally just not a good idea to do this. And I wanted to throw that out front in front of this movie, that while we talk about a terrible power supply, we should also talk about the fact that you shouldn't be plugging this stuff in anyway. On that note, people ask me, what do I use in my Commodore 64? Because that sits here in my lab with all of my gear. And I didn't even build my own power supply for my Commodore 64. I have one of Carlson's power supplies. You can see it right in the back there. And it's convenient because it also has a setup for 128. And that's one of the best power supplies, that you can purchase. So I just bought it, popped it in, and moved on. So that's what I'm using. So I have 3 power supplies on the table today. The first one here, this one I won't be opening. This one is potted, so obviously it would require some destruction to get this open. There are procedures to open these potted ones, empty them out, put a good power supply in, and close them back up if you're looking for, aesthetics and originality. But that's beyond the scope of what we're doing here today. But I just wanted to put this on the table as a demonstration. And this one is made in Singapore. You could see the 13th week of 83, right? This one also, I'll point out, even as it's potted, has no fuse accessible anywhere on this one. So for the AC side, if there's a fuse internally and it goes, I guess this one just, bites the dust, and that's all there is to it. The next 2 are able to open up. This one is made in Taiwan. This one is what I would call a serviceable unit. I could open it. It does have a fuse. This doesn't have a fuse outside. You actually have to open the box to get to the fuse. And we can see that this was made in the 11th week of 1983. On this third one, the placard has long since come off of it. However, this also is not potted, so this can be opened up. This one has an external fuse, as you can see here on the side. And we're going to be opening up this one too to take a look at the quality. You can see that this one is made in Poland. As we open up the power supply, the first thing we notice is there are in fact 2 fuses. Commodore 64 having AC and DC requirements as shown here, the 9-volt AC and the 5-volt DC, we end up with two separate autonomous circuits here, right? So we have a transformer here that's stepping down 120 volts or 117 volts, as it were, into two separate 9-volt segments right here. Or I know one is definitely 9 volts. The other one I'm going to assume is in and around 9 or less. I'll take a measurement. The problem is it's a no-load application, but that's just fine. Either way, the point is each of them has their own fuse. And you can see that it's not the same fuse. They have a different rating for each one. It stands to reason. Notice further that on the side that's being used for rectification for DC, for the 5-volt circuit, that there are only 2 diodes. It's not a full bridge rectifier. It's just 2 diodes doing this. So every expense it has been spared. And that is just the first observation, just opening this thing up. I've connected into the transformer here, and we're looking at the oscilloscope, and we're seeing 10.4 volts RMS. It stands to reason that would be a little bit high because I don't have 117 volts coming out of the isolation transformer. It's probably more like 120. So it'll be a little bit higher, and that's just fine. Yeah, the 9-volt is showing 11.2, and that's with the extra input voltage. And also remember that this is a no-load application. There's no Commodore connected to this. So if a Commodore was connected to this and there was current being drawn, it would pull down this transformer. There's no regulation here. So yeah, 11.2 for something like this seems absolutely fine. So keep in mind that as I observe this DC voltage here, this is also a no-load application. I got nothing connected to this. And that's going to change as we dive deeper into this and hook up some resistance onto this and draw some current from this power supply. Digging in a little bit deeper, we could see this 4700 microfarad electrolytic capacitor. No doubt filtration in support of the substandard rectification for this DC. So at least they beefed up the filter cap for this circuit. Aside from some other supporting hardware, a smaller capacitor, and a resistor, the star of the show is the 3052P 5-volt voltage regulator. And you can see for their part, the voltage regulator is mounted with some thermal paste onto this housing, to transfer the heat, and the housing is robust. I mean, it could transfer a substantial amount of heat to this housing. It's not free floating, it's not small, and it's very, very thick aluminum. So that portion was executed pretty good, I would say, as long as that screw was tight. And it seems to be tight on there. So for heat exchange purposes, this was done correctly. So again, we're looking at a no-load situation, and I'm measuring pin 2 on the voltage regulator, the input, to see what we got. And what I'm seeing here in the oscilloscope is 13 volts DC right there. And now I'm going to look at the resulting output of this no-load application. So I'm going to move the probe over. I've moved the probe over to the output pin, and this is the one that would make its way to the cable. And we can see that the resulting output voltage is 5.8, which would be for a Commodore dangerously high. I believe the threshold is 5.1, maybe 5.1 and a quarter. 5.8 is already bringing the RAM to death's door. This would be an unsafe power supply to run in a C64. I mean, this voltage, you're looking at it right now, this one would be a killer. Now, you could say that, well, yeah, this is a no-load application, so everything's running a bit higher because there's nothing bringing this down. Yeah, it's possible that the AC voltages would drop as the transformer was loaded down. But even if it was, this is a voltage regulator. Even if you lower the voltage down, I mean, it should still be 5-volt voltage regulator. That's what voltage regulators do. It's not regulating to 5 volts. It's regulating to 5.8. It's a failing voltage regulator. And you get to see this right here on the screen, 5.8. I'll note that under a no-load condition, having this on for about 10 minutes, if I get the laser directly on the unit, there's no change in temperature, or at least it's dissipating whatever heat's coming out of it. even though the difference in voltage is apparent, 13 to 5.8, the resulting value, there's still no current though, so there's no power. We'll take a look at this again when we get this thing under some sort of appreciable load. Interesting observation, I have the oscilloscope set up just before rectification. This is still the AC portion, and I'll take off the load for a second. I have a load set up for just about 1 amp, and I've removed it for now, so you can observe the sine wave that's coming in. This is AC 60 hertz, and now I'll add the 1 amp load at the end of the circuit here. We can see this flat top here, this distortion on the sine wave. So I saw that and I just wanted to point that out. It's actually 940 milliamps draw right now when we see that, and then when I pull it off, you see it restores and then comes back. So that's what we're seeing. This should come as no surprise to anyone. This is the rectified side, not having a full bridge rectifier. We saw the DC looks nice and clean when we had no load on it. Now I'm going to introduce that 1 amp of load and we will see what it looks like. There we go, we got a nice sawtooth on there. So it's quite terrible actually, and this could be a combination of a substandard power supply, which we have, as well as a less than ideally performing filter capacitor. But this is actually what it looks like, and this is just under an amp. This is only like 940, 960 milliamps. This is not nearly what it's expected to see, and this is already garbage. You consider this is for the 5 volts that goes to the ICs in the C64, and this is definitely not the type of 5 volts that you'd want to put into a computer and microprocessor and chips and what have you. So there you go. The filtering isn't actually taken care of by the time it reaches the voltage regulator. It's actually done on the output of the voltage regulator. We can see the input right here. We see around 11.6 volts, and the DC still looks like crap. The resulting value out of the regulator looks a lot cleaner. What effect that has on the regulator, I can't honestly say, but I'll admit that outside of the regulator already, you know, we don't see that the sawtooth in the waveform anymore. It looks like more like pure DC, albeit 5.6 volts. I want to get into the second power supply, and aside from the transformer, this one shares little resemblance to the first. This one is the one made in Poland. This one also has the 2 diodes in individual packages as seen here, and they're connected to the heatsink. This makes it also a lot more difficult to open this up to have a look, because they're tied to the heatsink, and the heatsink is soldered to the board. The large filter capacitor is in the middle, but you can see the 2 diodes off to the right-hand side. And onto the left-hand side is the voltage regulator. I'm going to take a look in there and see how big this filter cap is. Get in there and see the filter cap is a 4,700 microfarads, so quite a substantial filter capacitor. And I'm wondering why they would make the diodes in this type of construction, that type of package. I can't imagine why the diodes would require that kind of cooling, but and that's how they chose to do it. That's how they did it. So we're going to plug this one in. We're going to take a look at it. It is worth noting in this particular design, as I've mentioned before, that this one has a fuse that can be replaced externally, but there's only one fuse, and it is on the AC side, as we would expect. There is no fuse on the DC side of the AC portion before the rectifier. It just goes straight in, and if you know something happens, I guess that's it. Seeing a much higher input coming in. So 15.8 volts. This is before the voltage regulator, right after the rectifier. This is where I'm looking at right here. This is right after the filtering. This is the other side. This is the positive side of the electrolytic capacitor. Off of the other side of the voltage regulator, we're seeing just over 5.1 volts. This one looks good, you know, as far as what it's supposed to be doing. You can see I'm tied off the other side of the voltage regulator, right over there. So as far as usability goes, I would never use this power supply, but it's within parameters. Of course, we're going to load this down now with about 1 amp draw and retake those measurements we just took to see what it looks like. So here's what the DC looks like at the filter capacitor. As we expect, it's no longer clean with 1 amp draw. due to the substandard rectification, which we didn't expect to be any better than the last one given the components. That said, at 1 amp, the power supply is still holding. It looks okay. There's just really not anything wrong with this one. What I'd like to do is let it sit and take some temperature measurements. Well, that would also be exceedingly difficult. Number one, it does have very robust shielding around it, and number two, it's just hard to get in there with a laser because the components are so small and they're buried in there. I'll see what I can do. I'll let this sit for a while. So interesting thing happened. I'm measuring with my laser, and I didn't realize, in doing so, it wasn't capturing the temperature. It wasn't until I'd actually touched this metal to move it that I realized exactly how hot this was getting, and it cooled down now. And I don't want to say it was so hot that the whole thing was melting down here, right? But man, this thing was really hot. This had to be like at least 130 degrees. It was throwing some heat when I was pulling an amp, right? And it couldn't be seen because, and I guess it was reflecting off of the metal. I even tried putting this black magic marker on there. It didn't actually work, right? But this thing was cranking out some heat. And the interesting thing is when I was looking at it on the oscilloscope, the voltage wasn't going up. As it was getting hotter, I was watching the voltage fluctuating, but it was fluctuating downward. It was getting lower than 5 volts. And there are numerous reasons why that could happen external from the voltage regulator, right? But the interesting thing is, the amount of heat that this thing generates, and all of the heat was generating, on this side, on the regulation side. With that amount, that 1 amp that was being drawn and getting that hot and cooling down, getting that hot and cooling down, it's only a matter of time that something like this could be brought to failure. It wasn't anywhere near the maximum rated amount of current draw for this unit. And you could see that, earlier I mentioned, I said, wow, this is really robust, that it should be pulling that amount of current. And sure enough, it's almost not enough, heat sinking material for this thing. So, wow. And this is where it really all comes together right here. That thing gets hot enough, long enough, with enough heating cycles and just shorts. And that 5-volt regulation turns into that 13-volt input, and your computer's destroyed. And there's absolutely nothing that you can do to stop it. You don't know when it's going to happen. It's just a game of Russian roulette. This all comes back to the original question. Why would you want to use one of these in the first place? And the answer is you shouldn't. These are terrible power supplies, even in their day. It's been demonstrated that they're designed simple to be cheap, and that's the only thing that they're designed to do, to be as cost effective as possible, to do the minimum amount of what they're intended to, nothing more, right? If you insist upon using one of these without replacing the innards, I know Ray Carson has a device that goes in between these, which at least when these power supplies fail, will shut down the connection between this and the Commodore 64 when the voltage exceeds a threshold of, I believe, like 5.1 or 5.2 volts, right? So if you're going to use an original Commodore power supply, at least put one of these safety devices in between, or buy yourself a real power supply. The amount of time you're going to spend having to either replace a computer or repair the computer far outweighs the convenience, if in the short term, of just simply plugging in one of these old bricks and getting it to work for however long. So if you have one of these, unplug them, get rid of them, or gut them and upgrade them. But don't ever use them, because they're nothing but trouble, and they're going to cause you trouble. And saying that they haven't caused you trouble now is not a guarantee that they're not going to cause you trouble in the future. Every one of these will destroy every computer they're plugged into. It's a guarantee. Thanks for watching.